Okay, so here I am in R Studio, and I'm going to do a little demo with confidence intervals. Okay, so let me I'm going to run this slowly. Let me just see if this will run. Okay, so just ignore this part for a second. Okay, so this is a histogram of the population just on its side here. Okay, so this represents the population. It's a normal distribution here. And what I'm going to, and this line right here, this represents the mean of the population. Okay, and so this is the true mean of the population, but this, when we're taking a sample, we actually don't know the value of the true mean of the population. Okay, what we're going to see in a moment here, and I'm going to run it slowly at first, is you're going to see the computer take a random sample of 10 dots. Okay, it's going to be a random sample from this population. Okay, it's going to look kind of like this, but maybe a few more. And so these circles represent the random sample. Okay, after that, you're going to see a blue dot appear. The blue dot represents the mean of that sample of 10 dots. Okay, that's going to be our y bar. And then the computer is doing some calculations. It's going to calculate the standard deviation of those 10 dots. And based on the standard deviation of the 10 dots and the use of the t-star, or the critical value from the t-table, it's going to create a confidence interval. Okay, it's basically going to start at y bar, and it's going to go up the margin of error and down the margin of error. Okay, and so the confidence, so here's a sample of 10 dots. Here's my blue dot right here. This is my margin of error. Okay, I'm going down this margin of error and up this margin of error. Okay, so my confidence interval basically goes from here to here, which looks like, I don't know, negative 0.5 to maybe 0.9 or something like that. And so this confidence interval contains the actual mean of the population. Okay, so this confidence interval is, quote, a success in that it correctly, when we said I'm 95% confident about where the population mean is, that it's between here and here, it was actually correct. Okay, now here's another 95% confidence interval, and this is produced. The confidence interval is wider because the standard deviation of this sample is bigger. We see a larger range in this standard sample, and so it's bigger, and so it creates a wider confidence interval because that S part is larger. So the margin of error goes from here to here, and again, my confidence interval is wider, but it did actually contain the true population mean. Okay, so I'm just going to do this. It's going to run pretty slowly at first, and it's going to create, let's do 4 of these, okay? And so it's going to make 4 confidence intervals. Just do this. Okay, so there's the first one, 10 dots. There is the mean of those 10 dots, and there's the confidence interval. All right, here's another 10 dots. Here's the mean of those 10 dots, and here's the confidence interval. Another 10 dots. Okay, very spread out, but the mean is right there, and the confidence interval is right there. Okay, here the mean is down here, and when it creates the confidence interval, all of these confidence intervals happen to capture the true population mean of 0. Okay, is that good with everyone? Okay, so I'm going to speed this up a little bit. So I'm going to make, let's see if I can do 30, and let me just decrease the slowness here. So I don't know how long this will take. Okay, so here it's going across and it's doing a bunch of these, and it's making some confidence intervals. The computer's catching up with the work that it's doing. Okay, so here's 30. They actually all happens to capture the population mean mu. Okay, so so some of these we can see the population mean is much larger, and others it's much smaller, and a lot of them, the blue dots, are really close to the population mean. I'm sorry, the sample means are some can be close or far, and let me see if we can look at this. Okay, so some of the samples there's very little spread. Okay, and so the confidence interval is pretty small. Okay, some of these other samples, the spread is pretty large, and so the confidence interval is quite wide. Okay, do you see that? Okay. Let me just try running another 30, and we'll see what happens. Okay. I'm waiting for one to miss the population mean here. Okay, there's one. Okay. So here's one where, because of just the nature of random sampling, it happened to get a mean that was way out here, and even though it made a confidence interval, the confidence interval does not capture the population mean mu here. Okay, and again, when you are doing a study, okay, you have no idea if your sample is this, where your sample mean is very close to the population mean, or you have no idea if your sample is this one, where your confidence interval does capture the population mean, but just barely, and you have no idea if it's this one, where your sample mean is just way out there, and you create a confidence interval, and it's way off. Okay, so you have no idea which sample is yours because you just have one sample, and you have no idea what the population looks like. Okay. And so what this shows you, by doing this a whole bunch of times, it shows you that, well, we didn't have as many errors as I expected, but with a confidence level of 95%, in general, about 95% of the confidence intervals we produce will capture the population mean mu, and about 5% won't. Okay, and so you're banking on the fact that your confidence interval has the population mean. Okay, and again, that you're banking also on the fact that the sample means come from a normal distribution. Okay, that's the other part that goes into it. If the sample means don't come from a normal distribution, you can't make confidence intervals that are meaningful. Okay, I mean, sure, you could plug in numbers into the formula, and you're going to get some other numbers, but it really contains no actual meaning here. Okay, and we can see I can make confidence intervals for a uniform distribution. here is the uniform distribution showing that all numbers are equally likely, and we're getting some quite a diverse range here. Okay. So sometimes our blue dot is close. This one barely managed to get the population mean. Yeah, okay. It's not missing. I wonder if I coded this poorly, where I'm expecting it to miss the population mean a little bit more often than what we're observing here. But that doesn't seem to be the case. I don't know. Okay. Oh well. I'll have to inspect my code a little bit more. But so, and again, so here's a confidence interval where the mean is 10, and it's going. So we get kind of a different situation here. Okay. So anyway, yeah, I probably screwed something up in my code, but the general premise still holds true in that here where you're pulling 10 dots, okay, or a sample of size n, and we're plotting the sample mean at the blue dot, and then creating a confidence interval. I can change the size of my sample, so rather than taking samples of size 10, I can take samples of size 5, okay, and notice, I think the overall scale is still going to remain the same, but here, because I'm only taking 5 dots, we're seeing that the confidence intervals are much wider, because probably my standard deviation could also be much bigger or smaller, because it's not as good of an estimate as using 10. And then my standard error is also much larger because I'm doing s over the square root of n. And my square root of n is going to be a smaller value, so that thing is also going to get larger there. Okay, so that is, I don't know, kind of a little neat demo that you can do with R stuff here. I'm not expecting you guys to figure that out. It used to be a lab, but you can thank your the classes before you and their feedback who said this lab was not useful. They just said that the demo in class was good enough, don't make us do it. So I'll figure something else out. Okay. I think that's it. We have a quiz next week. So I think there's a little description of what you need to know on the website, and then we'll see you then.